Hello everyone. In this video, we will learn to balance a redox equation in acidic medium and basic medium using half reaction method. Some redox reactions are too complicated to balance by trial and error method. We are going to discuss a method called as half reaction method to balance those complex redox reactions. This method is called as half reaction method as it involves splitting a redox reaction into two half reactions. This method of balancing works only for those redox reactions that occur in aqueous solutions. The redox reactions that occur in aqueous solutions either occur in acidic or basic solutions. The acidic solutions have excess of H plus ions and basic solutions have excess of OH minus ions that take part in the reaction. First, let us learn to balance a redox reaction in acidic medium. That is, the reaction is occurring in an acidic solution with excess of H plus ions. Let us say we need to balance the following equation. MnO4 minus in aqueous solution reacts with Fe2 plus to form Fe3 plus and Mn2 plus. And let us also assume that this reaction is occurring in acidic medium. The first step is to assign the oxidation numbers to each atom in the reaction. For oxygen, it is -2. Manganese, we can calculate it to be +7. Iron, +2. If we move to the product side, for iron 3 plus, the oxidation number is 3 plus. And for manganese 2 plus, the oxidation number is 2 plus. Next, we need to identify the oxidation reaction and reduction reaction. As we can see, the oxidation number of iron increases from +2 to +3. So we can say iron is undergoing oxidation. The oxidation number of manganese decreases from +7 to +2. Therefore, we can say that MnO4 minus is undergoing reduction. Now that we know the details of the redox reaction, let us start the balancing process. The first step is to write the equations for the oxidation and reduction half reactions. That is, we split one redox reaction into oxidation half and reduction half reactions. Iron changing from +2 to +3 is the oxidation half of the reaction, and permanganate ion, that is MnO4 minus, changing to Mn2 plus is the reduction half reaction. Next, for each half reaction, we perform the following steps. A. Balance all the elements other than hydrogen and oxygen. For the oxidation half of the reaction, we have one iron on the reactant side and one iron on the product side. Therefore, all the elements other than hydrogen and oxygen are already balanced. For the reduction half of the reaction, we have one manganese on the reactant side and one manganese on the product side. So it is also balanced. In the previous step, for each half reaction, we balanced all the elements other than hydrogen and oxygen. Now, we balance oxygen by adding water molecules on the side that has fewer oxygens. For the oxidation half of the reaction, there are no oxygens to worry about. For the reduction half of the reaction, we have 4 oxygens on the reactant side and 0 oxygens on the product side. Therefore, I will add 4 water molecules to the product side, which balances oxygen atoms. Next, we balance hydrogen atoms for each half reaction by adding H plus ions to the side that has lower number of hydrogen atoms. Note that we are adding H plus ions because the reaction happens in acidic medium and we have excess of H plus ions floating around in the solution. For the oxidation half of the reaction, we don't have any hydrogens to worry about. Now let us look at the reduction half reaction. We have 8 hydrogens on the product side and 0 hydrogens on the reactant side. So, to balance these hydrogen atoms, I will add 8 H plus ions to the reactant side. So far, for each half reaction, we have balanced all the other atoms except hydrogen and oxygen. Then we balanced oxygens by using water molecules. And then we balanced hydrogens by using H plus ions. Next, we balance the charges using electrons. For the oxidation half reaction, the overall charge on the reactant side is +2 and the overall charge on the product side is 3+. We balance the charges by adding electrons. Now electrons will be added to the side in which there is greater positive charge. For example, in this case, if we add 1 electron to the product side, the charges now are balanced on both the sides. That is, 2+ charge on the reactant side and 2+ charge on the product side. Now let us balance the charges for the reduction half reaction. First, let us count the charges on the reactant side and product side. On the reactant side, I have 1 negative charge and 8 positive charges. So overall, we have 7 positive net charges on the reactant side. On the product side, we have only 1 charged species with an overall net charge of 2+. So, we have 7 positive charges on the reactant side and 2 positive charges on the product side. We need to add electrons to reduce the positive charges on the reactant side. And we need to add 5 electrons to balance the positive charges on both sides. So, we have balanced all the atoms and charges for both the half reactions. Now let us look at each half reaction. The oxidation half reaction is releasing 1 electron and the reduction half reaction is accepting 5 electrons. The electrons released in the oxidation half reaction must be equal to the electrons gained in the reduction half reaction. To equalize these electrons, we multiply either of the half reactions with an integer. For example, in our case, for the reduction half reaction to occur once, the oxidation half reaction has to happen 5 times. That is, we need to multiply the oxidation half reaction with 5. In the fourth step, we add both the half reactions and cancel identical species on both sides. The following is the combined equation. Let us check if we have any identical species on both sides. We have 5 electrons on the reactant side and 5 electrons on the product side, which get cancelled. So the remaining equation is a balanced redox reaction. In the last step, we verify if all the atoms and charges are balanced or not. We have 5 irons on left side and 5 irons on the right side. 1 manganese on the reactant side and 1 manganese on the product side. 4 oxygens and 4 oxygens on both sides. 8 hydrogens and 8 hydrogens on both sides. All the atoms are now balanced. Let us now look at charges. Let us calculate the total charges on the reactant side. We have 5 times 2 plus minus 1 plus 8 times plus 1. A total of 17 positive charges. On the product side, we have 5 times 3 plus 2 plus. 17 positive charges on the product side. The charges are also balanced. So this is how we use a half reaction method to balance a redox reaction in acidic medium. Note that the reaction consumes 8 H+ ions that are available in the acidic solution. Now, what if the reaction were to take place in a basic medium? A basic solution does not have excess H+ ions floating around in the solution. Instead, it has OH- ions. Let us now discuss balancing the redox reaction in a basic medium. Let me first copy the balanced reaction in the acidic medium. As discussed earlier, there are 8 H+ ions consumed in the reaction. And in a basic solution, we do not have H+ ions. So, we need to get rid of H+ ions. So, what we do is add OH- ions to both sides. In this case, we have 8 H+ ions. Therefore, I add 8 OH- ions on both sides. So on the reactant side, 8 H+ ions and 8 OH- ions can be combined and written as 8 water molecules. Next, we eliminate as many water molecules as possible that are common on both sides. If we look at the above equation, we have 8 water molecules on the reactant side and 4 water molecules on the product side. So we can cancel 4 water molecules on both sides. And this is the balanced redox reaction in basic medium. So if you need to balance the redox reaction in basic media, first you do as if you balance the reaction in acidic medium, then take the reaction and add OH- on both sides and cancel as many water molecules as possible on both sides. The resultant reaction will be a balanced redox reaction in basic medium.